Okay, welcome. This is our 1 o'clock press conference. We're calling it Reducing a Major Climate Warming Agent from the Atmosphere. Exciting progress on two fronts. And our speakers are in the order that they're going to speak. V. Ramanathan. He's a distinguished professor of climate and atmospheric science at the Scripps Institution of Oceanography at the University of San Diego in San Diego. And Nithya Ramanathan, who's assistant research professor of computer science at the University of California, Los Angeles.
Thank you. So the overall topic is on black carbon. And there are two parts to this. The first one is new findings on major reductions in black carbon, statewide reductions in black carbon in California. And sort of tomorrow there is a talk I'm giving on this topic, and then there's a paper on this, which is hopefully be put online tomorrow in the atmospheric environment. So the question is, why is it such a big deal reducing black carbon over California? I mean, we should just treat it as a local issue, or are there global implications? And that's a part I'm going to touch on to point out that this is indeed has major implications for mitigating climate change on global scale. And that's a part I'm really interested in this research. And so going to that, and then it'll be followed by Nithya Ramanathan. I don't know who she is, but she's going to talk about how to make measurements of black carbon on a global scale. And then the reason it's such a big issue is that the lifetime of black carbon is so small, I mean, it's short, few days to few weeks. And the sources are so vastly distributed from an individual hut in remote parts of India and Africa to trucks in California. So how do you monitor this? So that's the issue she would talk about. So the first thing is, so this is the main result in that paper. And what it shows, it's a little bit of a complicated figure. And if you just focus on the black line there, that shows the black carbon, how it has come down. Yes, thank you. Black carbon is basically the dark stuff you see coming out of diesel trucks. I mean, it's known as soot. The only distinction is soot has few other compounds in addition to black carbon. So black carbon is the particulate. Anytime you can see something, if a pollutant comes out as a gas, you don't see it. But it comes out as particulate, then you see with your eyes because it's absorbing light, it's scattering light. And the other major source of black carbon is biomass burning. We know that in California with our forest fires and numerous other sources. Okay? The major sources in terms of California is diesel, both on-road and off-road vehicles like tractors and farm equipment. And then biomass burning. And the third is residential cooking. Barbecuing, etc. So, like I said, black carbon is a particulate, okay? And we are also showing that as, about 50% reduction over the last 20 years, the emissions from diesel has come down. So there are two things here to remember: what comes out of the ground from our vehicles and what stays in the air. And we are showing both of them have come down, and which is, for a scientist, it's a spectacular controlled experiment, whereas we can see the effect of our policies, okay? And the bottom one just takes that data. I'll show you the stations that takes that data or different parts of the state, southern, central, northern, and it shows it's a statewide decrease, okay? It's nothing to do with a local issue. So, and our paper shows it was generated as a consequence of California's aggressive laws to reduce particulate emissions. And starting from, in fact, the laws, we'll talk about this if you're interested, it started in the 1970s, in which we decided to cut down the smoke. Okay? And then there was an acceleration starting from 1988 to 1990, and that's the thing we saw as a major decrease. And the California data has global implications. And why do I say that? So let's look at the quick figure. This comes from the IPCC. Shows globally the heat trapped by various pollutants. Of course, carbon dioxide is a major one. The size of the pie shows how much heat has been trapped by each one of them. Well, you've all heard about carbon dioxide, and there are other pollutants, the gases, methane, HFCs, nitrous oxide, ozone, and then black carbon. So it turns out these so-called non-CO2 climate pollutants, as of 2005, have trapped as much as 80% heat as carbon dioxide. Okay. And you can see black carbon is a non-negligible part of that trapped heat. And while our steps to mitigate CO2 emissions have faltered, and we have lost much valuable time in the last 20 years, these things can complement it. Okay? And why is that such an issue? It turns out this, I'm just showing you my own calculations, but there are also other papers published by various groups. And we scientists have concluded if we continue on the current path of emissions of greenhouse gases, we are going to reach the 2-degree threshold, which many considered is the threshold or the guardrail for what one considers unmanageable or dangerous climate warming. So we're talking about the next 30 to 50 years. Hopefully, Cancun has had a modest success and will continue, but we find it's not enough just to cut CO2 emissions, even if you cut it by 50%. On the other hand, if you bring in the other pollutants, then we have a chance to delay that approach to that guardrail by anywhere between 20 to 30 years. And hopefully, that would give us added time for revolutionary changes in our energy consumption. So another thing is called short term. Why is that? Because these compounds live for a few days to a few weeks. Just like we showed in California, we used our laws to mitigate these other gases, they'll be gone weeks, months, years from now. So we have a chance to see some quick global response. Okay, so that's why I'm personally very excited about the California data. So this shows the mitigation, the long term, and the near term. Carbon dioxide, as you know, stays for centuries once you put it. That's why it's important to cut it down. And the near term comes in that if you cut them down, you bring down the heat trapping effect, and you can delay that large unmanageable warming. And I have been looking for a control case where we can show. You see, the claim I'm making, pollutant lasts several days, and cutting down, will give you quick relief, and that's where, the California data, this again, this all published paper, it's not new result, to show the black curve is what if you cut down all the non-CO2 climate pollutants, okay? The key thing is there are technologies available, right? And it can be done locally and nationally. That's what California has shown. These are off-the-shelf technologies or so-called shovel-ready projects. And what was interesting about this, linking about the climate, this is what a mitigation person's dream would be. There are many pollutants we put. Some are scattering light and cools climate, like nitrates, sulfates, organics. In the California case, what we find is that selectively, just black carbon has come down because diesel vehicles emit mainly black carbon. Okay? So what it shows is the ratio of you can think of the BC, non-BC's ratio of warming and cooling aerosols, and that ratio is coming down. And we have used data to show the right-hand side is how much heat trapped has come down, okay? And that shows that has almost come down by 0.15 in 1990 to come down to about 0.07 factor of 2. Selectively, we have withdrawn heating aerosols, okay? And then we talk about its impact on radiation and all that. So these were the claims we were making last 5 years on near-term mitigation. And the California data comes as first a proof to policymakers Yes, the technology is there. Yes, if you have proper laws and deploy the technologies, yes, the black carbon can come down. Okay? And so, that was, I'm hoping that with the publication of the paper, Dr. Bahadur is the first author of this study, and it was done in my team. This will hopefully start a new major modeling study for climate models to see if they can simulate this data. Okay? Put these technological changes in California and see what do they predict. And in the other things about these short-term warming, they're also air pollutants, okay? So the black carbon, when it's removed by snow, rainfall, so when it is removed, it falls on bright surfaces like the Arctic sea ice and the Himalayan glaciers. It darkens them, meaning it absorbs more sunlight. In fact, there are numerous studies which have shown maybe as much as half of the Arctic melting of the sea ice and snow may be coming from black carbon deposition. And in fact, one of my students, she's at Lawrence Berkeley Lab, has collected samples over the Sierras, 2 stations or 2 years, and we showed the snowfall is very effective in removing black carbon and dumping it on the mountains. Okay? And the other is the soot is linked to over 1.5 million deaths globally. And I don't know this reduction, how much it has improved on the health of California. It will be an important study to find that. Has it had impact on reducing premature deaths? With that, see, those are the stations. That's one of the beauty of the California being on the front line of this air pollution regulation science. They have fantastic stations, okay, and collects not only black carbon, other compounds. And so there's a long time history of over 25 years. So we were lucky we didn't collect that data, we were lucky to access the data and use it. So what we want to show, the next one, and then it's open to questions, is, well, if this catches on, globally there is an effort to reduce black carbon. How would we measure them and document it? Okay, a lot of more than half the black carbon emissions come from in the Asian region, and some from Africa and South America, with the biomass burning. How would we document it? So we have our next speaker to talk about that.
Hello. So I'll be talking about a new instrument that we've developed to monitor black carbon at mass scale using cell phones. So we've developed this new instrument using cell phones, and one of the main advantages of what we've done is that it doesn't require connecting any expensive, difficult hardware to the cell phone directly. It doesn't require any software running on the cell phone. This instrument will work with any cell phone that has a camera. So the idea behind the instrument is that there's a sampler, a low-power sampler that we work with that exposes particulates onto a filter. Once you have that filter, a cell phone can be used to take a picture of that filter. And that picture can be emailed to our servers, which could be in the cloud, running anywhere. And that picture is analyzed in order to determine the black carbon concentration, the ambient black carbon. So what are the advantages of using a cell phone? Well, there's 4 to maybe almost 5 billion cell phones in use right now. And almost all of them that are being manufactured today come with cameras. So the camera is a sort of a nice interface to be collecting data with. The other thing that we found is by enabling this mass scale data collection, we found that it's beginning to engage citizens in public health, in environment, in understanding the climate and the impacts. So there's 2 main innovations that made this instrument possible. The first is that we determined that actually the color of the particulates on the filter correspond very closely with the loading or the concentration of the particulates on that filter. So if you look at the picture on the left of the slide, you see a picture of our sampler, And right below that, I've included just a set of 6 sample filters, which increase in black carbon loading from left to right. And you see that the visible color darkens as the concentration increases. And so in order to systematize that, we took a set of about 25 filters and we scanned them in using a standard image scanner. And what we found is the plot on the right, which essentially shows color on the x-axis extracted from the scanned image compared with the actual black carbon loading that was on the filter. So you see that there's a very tight correlation between the two. So that was the first discovery that made this instrument possible. The second is, once we know that color corresponds with black carbon, the question is, how do we then translate that to an image of the filter? So if we don't have access to the filter directly, which in most cases we won't, how do we make this data collection scalable? So in order to be able to take a picture, as most people know, cameras differ. Every cell phone has a different configuration. Every camera has a different configuration. And so in order to compensate for that, we had to come up with a reference scale. So if you look at the top left of this image, you see a reference scale of shades of gray varying from light to dark. And what we did was we designed a scale where we knew what the black carbon loading was associated with each of those shades of color. So now, when anybody takes a picture of a filter, they put it on our reference scale, they take a picture of it, and the idea is that the light will equally impact both the filter as well as the reference scale. So when the image is then analyzed by our computers, the computer algorithm first seeks out the reference scale, extracts each shade in there, and then can essentially recreate the calibration curve. It then extracts the color of the filter and just plugs that color into the calibration curve. And from there, the algorithm is able to determine what the loading is on the filter. From there, given the exposure duration of the filter and the pump flow rate, the algorithm can then calculate what the ambient black carbon concentration is. So this is what makes it possible to measure black carbon, essentially using any cell phone with a camera. So we've done some measurements in California and India. We've collected about 80 samples, and we've done side-by-side comparisons. We've compared with both an optical method using an ethylometer in order to compare the results we get with our cell phone. We've also compared with a carbon mass balance method with a filter-based thermal optical analysis method. And we found both in California as well as in India that our measurements were within 10% of these reference instruments. So what was remarkable about that result is that the black carbon and the source of black carbon in these two environments is different. There's different organic carbon ratios and different sources, but still we were able to use the same reference scale in order to collect measurements in both California and India. And so this high accuracy that we've gotten so far really does demonstrate the potential for this instrument for global black carbon monitoring. And what's the need for sort of high-resolution black carbon monitoring? Well, one of the uses would be to validate black carbon mitigation actions in India, for example, where clean cook stoves are being introduced in the country to reduce black carbon. We're starting to use these cell phones in order to collect measurements on an individualized household level. The other idea would also be to reduce uncertainty in emissions inventories, where current gold standard inventories report an uncertainty of up to 100%, and to validate air pollution, health, and climate models. And one of the reasons that we need these localized measurements is because black carbon is emitted by highly localized sources, and because of its short lifetime, requires many measurements taken spatially distributed. So that's it. Thanks.
Okay, can you hold on just a sec? Who has a question? Eli?
So just explain how you do it. Does the measurement get done all the time? Is the machine just sitting in and is it indoors? Is it outdoors? once a week you take the filter off and take a picture of it. Just explain the basic procedure.
So it could be running indoors or outdoors. The frequency depends. So it depends. In one of our projects, we'll be putting it indoors. That's in India, where we're measuring the emissions of cook stove interventions. And so there we're looking specifically at indoor reductions in black carbon. But for example, we have a contact at JPL NASA where they're interested in measuring outdoor black carbon concentrations, so they will be putting it outdoors. And in terms of the frequency of collection, it actually depends on a couple of things. It depends on the concentration, because there is a saturation region. At some point, if the particulates get too dark, we can't really distinguish between concentrations. So we've been using 1 to 2 or 3 days. In California, we were able to change it almost every 3 days. In India, indoors, we really had to change the filters once a day. The other thing is you could adjust the flow rate. But yeah, and actually in the plot, I didn't mention this, but if you look at the plot that I showed here, what was really crazy was that the bottom left is data. It's around 1 microgram per meter cubed. All that data was taken in California. But if you look at the data on the top right, and the left is a log scale, this was just taken from a random village, and the concentration got up to 100 and sometimes even 1,000 micrograms per meter cubed. And these were daily averages. So this is not even like a point, single point. So huge difference in the concentrations when you look at indoor in India in a standard village household with sort of standard ventilation compared to Los Angeles. And those Los Angeles points, some of those were taken within a mile of LAX. So
the black carbon escapes from the house through a chimney or something, or through the windows. I mean, how much of a climate effect does it have if it's since it just kind of falls after a while, right?
Right. First is, in most of these homes, there are no chimneys. They are huts. So they're really inhaling all of this. And what the lung doesn't inhale goes to the outdoor environment. And roughly about 80–90% is outdoors. And if you look at a satellite image during the dry season, between October to May, you can just take any single day, you'll see the entire Indo-Gangetic Valley, starting from Pakistan all the way across India, Nepal, Bhutan, going into Thailand. You'll see this vast plumes of cloud, and I call it atmospheric brown clouds, or ABCs. Yeah, so in fact, if you look at California, the residential burning, fireplaces, cooking, is probably about 5 to 10% of the total black carbon emissions. But if you go to South Asia, it's almost 2/3. So there, cutting down the cook stove emissions will have a major impact, not only on indoor, but outdoor air quality. And climate, regional climate changes. Yeah, ultimately it escapes from indoor to outdoor.
Ann Rosenthal, SF Nature. I'm very interested in what the cost of this might end up being, because I know as a resident of Palo Alto, California, I'd be very interested in being able to test my own neighborhood. We have a large concentration of homes with wood-burning fireplaces, and because my husband has asthma, we actually can't keep the windows open at night in the wintertime. And it would be very interesting to be able to document exactly what people are breathing. So I'm wondering, would this, say, a few years down the road, be available as a kit?
Yeah, I forgot to actually mention, part of this was to develop something that was low cost and also ultra low power. So the idea being that while it's not an effort to try to replace existing gold standard methods, it is orders of magnitude cheaper in order to make it available in a more accessible way. We were thinking, more developing countries perhaps, but we've started working actually with some communities in East Los Angeles that are interested in collecting black carbon data. So we're hoping in the next 3 to 6 months to be able to start that. And so to answer your question, the cost of the sampler right now, and this is, sort of our first version, all of that, it's about $500 to $600. And then each filter costs about $1. And then the processing is free. You just take a picture with your cell phone and email it, so that's simply the cost of your data plan.
Harvey Leifert, freelance. It's not a very well-formed question, but first I have a preliminary one. Are your slides available somewhere that we can get?
Yeah, actually, I think Annie has a USB stick.
Okay, thank you. The actual question, I'm trying to put these two things together. These are really two very separate studies. One is on how you might find out how much black carbon there is. That's Nithya's program. And Ram's is a survey of what has actually happened over the last 20 years in California.
Right.
Without reference to that study, it was presumably done by other means.
Yes.
Now, what are the specific laws that came into effect in California that had these dramatic results? And are there similar laws in other places, already existing laws, that you could also test to try to replicate this?
Thank you, Warren. Just as to declare, I'm not going to mention it, Nithya is my daughter. So 2 or 3 years ago, during Thanksgiving, she was telling me all the exciting things she's doing with computers and cell phones. So I told her, why don't you do something useful? And that's, in part, that's how this got started. Yeah, I think in terms of California, the laws which contributed to this really started in the 70s. Okay, I think at those days, the primary concern was smoke from these diesel trucks. And so a series of things were put together, engine modification, fuel control, cutting down the sulfur in the fuel, right? And also the diesel fuel mixture. So that had a dramatic impact between 70s to 80s. This was documented by a study at Lawrence Berkeley, Tom Kerstetter. And then between 70s to 80s, just because of the old engines were going, turnover, the new vehicles were coming, they still continue to see the decrease. And then started in late 1980s to early 1990, when the push was for really low sulfur fuel. I think the law was to cut it from, it was I think more than 2,500 ppm of sulfur, and it was cut down to 500 ppm, really low sulfur, or ultra low sulfur, whatever they call it. And that had a major impact, okay, because sulfur, the SO2 apparently, I'm not an expert on this, I'm just quoting what I read. The sulfur, of course, in the engine gets SO2, and then the SO2 reacts with the aromatics and other compounds and then contributes to the soot emission. So if you cut the sulfur emission, apparently the aromatics went down as well as the black carbon. But no one really documented the black carbon because the interest those days was on health. And so they didn't know what exactly was causing the health. So it was generically used PM. As you know, PM is the total particles, right? That was all they were measuring. But they were measuring the aromatics. The PAH, polycyclic aromatic hydrocarbons, was a major health issue. So the focus was in cutting those two things down. But just fantastically and inadvertently, it cut down black carbon because most of the particulate emission from diesel is black carbon. So, in answer to your question then, change of fuel composition, change of engine design and catalytics, okay? And then switching over to ultra low sulfur contributed to that. And this, of all the not so good stories we hear about environment, this thing keeps getting better and better. As of 2005, There's a new requirement to put diesel particulate filters. That'll pretty much cut the black carbon emission from diesel to near zero. So that's just starting, the diesel particulate filters. In fact, in Germany, it's a major push because a lot of their cars are diesel. For example, in Berlin, you can't drive with anything without DPFs, diesel particulate filters. So, sorry, did that answer your question? Or?
And the climate impact of all this as well.
Yeah. So let's talk about the 3 pie charts I showed. That's basically IPCC result. The greenhouse gases warm the planet by trapping the infrared heat coming from the surface and atmosphere. Just like a blanket on a cold winter night keeps you warm, not because the blanket gives you heat, it traps your body heat. That's how the gases work. Whereas the black carbon traps the incoming sunlight. Okay? So it absorbs, that's why it's black. Anything darker substance absorbs more than lighter substance. So the planet reflects on average 30% of the incoming sunlight. So black carbon blocks some of this, radiation which would have otherwise gone off to space. So there are 2 separate things, and I think this so complex picture, I give this blanket metaphor. So the planet is warm not because of human impact. Nature gave us a greenhouse blanket. That's water vapor and carbon dioxide. All we are doing is thickening that blanket. Okay? Now think of black carbon as smoke in that blanket. You're filling the holes in the blanket. You're trapping sunlight. You're preventing sunlight from escaping. Okay? So the blanket prevents the infrared heat from escaping, and the smoke in the blanket prevents the sunlight from going back. So, it does, but you see, remember, the way you modify the planet's climate is change the way it exchanges heat with space. Okay, so think of this blue spherical ball, right? Its basic energy source is sunlight. Not all of the sunlight is absorbed by the planet, about 30% is reflected by snow, by clouds, everything. And the black carbon absorbs the incoming sunlight, and importantly, it sort of absorbs the sunlight which was reflected, which would have otherwise escaped to space. So it's trapping heat inside the system, sun's heat. Sorry, let me finish, Eli. I think he's still...
you guys can have that discussion afterwards, maybe, so we can have other questions.
Dr. Ramanathan, John Cox for Discovery News. You used to observe that the soot, the black carbon, you thought was masking a certain amount of incoming radiation, and that as you cleaned the air of black carbon, it was actually going to cause an increase in the effect of warming.
Thank you. Remember, you're the ones who are making the picture complicated, so I need to give you one more detail. The particulates we emit, soot is only one of them. The other is sulfates. Remember, from coal combustion, you put out sulfur dioxide, and that SO2 gets converted to sulfates, particles. That's the whitish haze you see on major industrial cities. Okay? The black carbon makes it brownish. So then, going back to the blanket, you put smoke in the blanket, you're also putting mirrors on the blanket. The mirrors is bouncing the sunlight. And what are those mirrors? Sulfates, nitrates. So just to finish that story one more, the IPCC says these mirrors have masked almost half of the warming. And the question is, why is North America and Europe warming at a rapid rate last 25 years? Many scientists believe it's because we are cleaning up the air by cutting down SO2 and NOx. And that is why I'm excited by the California example. It is drawing down the heating aerosol. So that's what I've been pleading. By all means, reduce sulfates and nitrates because they are pollutants. They cause acid rain. But don't take the mirrors and leave the smoke behind. take both of them out.
Do we have other questions? Eli, would you talk? Grab the mic. Thank you.
Ram, could you go to the slide where you have the, forget what you call it. It's,
I need our
you.
technologists to help us switch.
Go back again.
Go back. Tell me when to
That one.
That it? Yeah.
Okay, so if you could just talk about the 1.4 as a value, how significant that is, since that's the takeaway number from this paper, and how did you get that number? And also, can you transfer that? Can you express that number in temperature? Did it, in terms of what it would have been warmer in California?
Let me give you a reference point. The temperature is a different story. Sorry. If you look at the total sunlight, solar radiation absorbed by California, it's about 200 watts per meter squared. So we have almost, 50 years ago, 20 years ago, by having more black carbon, we are absorbing about 0.5 to 1% more sunlight. So we have brought it down, okay? And the reason it is difficult to convert into temperature, just for this, we need huge climate models, is that this is not the only thing has changed. And the greenhouse gases have been increasing, sulfates have been decreasing. As you know, our California climate is influenced by, during El Nino, what happens in the Pacific Ocean. So to address the question, how much they helped California temperature, I need to know what happened in the entire world. We know from the El Nino example, right? The El Nino is a warming in the Pacific Ocean, tropical Pacific Ocean, thousands of miles away. So the temperature is a separate issue. I'm not saying it can't be addressed, but it needs more fancy climate models and all that. So to give you another reference point, sorry, go ahead.
What about the radiative forcing in California from greenhouse gases? Can you compare the radiative forcing from your black carbon, which you've just come up with radiative forcing from?
If you look at the, I'll give you the number, but we have to be careful about interpreting it. If you look at the total greenhouse energy trapped by the greenhouse gases over California, it's of the order of 2 to 4 watts per meter squared. So this is about half. But remember, the greenhouse energy trapped by California is carbon dioxide emitted by the whole planet because it lives a long time. The CO2 above our head is not just from locally emitted, it's from the entire planet. Whereas black carbon, since its lifetime is few days, I would venture the near surface black carbon is almost all of it locally emitted, but we have made measurements, with aircraft. We run unmanned aircraft with black carbon instruments. Once you go above a kilometer above our head, during springtime, in the springtime, almost half of it comes from long-range transport from East Asia. So while before we start blaming the Chinese for all our problems, half of our black carbon goes downwind, right? So by cutting down our black carbon, we have really protected the rest of U.S. because the wind goes from west to east.
Other questions?
By the way, all these questions, I'm forming another paper I need to write. These are things I have not explained in my papers.
If the question's just going to be you guys having a discussion, maybe we could just end the press conference and you could just go up there and talk to him directly.
All right.
Is there anyone else with a question?
Yeah, well, it's a little more general. It was the second part of the question I asked before that I don't think you got to. The laws that came into effect early in California have pretty much been adopted throughout the U.S., or they're national standards now, I think. And I wonder, first of all, if that's the case. And secondly, if so, has the same effect been noted elsewhere as has been noted in your study here in California?
I'm not an expert on that. I wouldn't want to comment on it, what's happening in the rest of the U.S. You're right. Now, if you look at the total black carbon emission over the U.S., it's come down, but I don't know how much of it is from what laws, what sources. And certainly, hopefully, our study would encourage other scientists around the U.S. to look for each of those states. So one thing I would guess, though, if you go to the eastern coast from Ohio Valley onwards, you will see a major decrease in sulfates. So you're not going to get this thing where we just have black carbon decrease. So it will differ from state to state. And I don't know the answer to your question, but nationwide.
Hi, I'm Andrew Friedman from Climate Central. You've written papers before talking about the potential for global mitigation of black carbon and its benefits for both the Arctic, the Himalayas, and elsewhere. Right now, in the policy-making realm, obviously the California example is an interesting case study of a statewide reduction. Where do you see the most promising prospects, I guess, for mitigation? Like, which international forum are you and your colleagues looking at? Is it the UNFCCC process? Is it more under Montreal, another agreement, or just sort of in general trying to talk to key policymakers and make them aware? I'm just not sure where to keep an eye out for action on this.
Right. As you know, my role is I'm a physical and natural scientist, so I see more of my role as informing and pointing out success stories. But I did write this op-ed in New York Times with David Victor. So I think in our view is all of the above. That's the beauty of the black carbon issue. Or the other short-lived climate forces. Methane may be slightly different. The whole world need not agree. Because, I think this is where the local benefits nicely interface with global goods, if I can use that phrase. So we want to do it for our own reasons, right? I mean, India wants to do it to cut down the Himalayan glacier pollution. Arctic nations wants to slow down the Arctic warming. So each of the region will get to see local and regional benefits. So if UNFCCC can be done without detracting attention from carbon dioxide issue, which is the issue, fantastic. The HFC's Montreal Protocol could be a good venture. But I think on the black carbon and ozone, that's a major greenhouse gas. As you know, ozone is a big problem for California. They could be done by the EPAs of the world. And so I'm talking with some of the nations, particularly India, to see if they could visit with the California Air Resource Board and start some collaborative programs to see how did you regulate this, what laws worked, what technologies worked.
Okay, we have time for one more question, if there's anyone with one.
Bas den Hond, Economist. I'm trying to connect the two issues of indoor black carbon and the one that influences the climate. If I understand correctly, then a person in India who doesn't have a new clean stove handy would do well to ventilate his hut very well. If everyone did that, would then the climate in India be influenced, or would it be so local and so slow moving that actually it's a totally different thing?
Right. Good question. I think the cell phone development started because we have this project called Surya, where we are trying to find out how much of the heating and cooling aerosols are emitted by indoor cooking. And then it's a scientific intervention project. We collected data for 1 year, and then about 4-6 months ago, we switched the cooking, with all the women helping us, to technologies which cut down black carbon emissions. And we are trying to see what benefits is there, what is the impact on global warming from this. We don't know the answer to that. it's in that context, Nithya's technology, because we didn't have enough money to do this project. My black carbon instruments, they all cost from 15 to 1,000 to 50,000. And we wanted to find out what's happening in every hut. There are 500 homes. So that's where the necessity, if we can use a cliche, necessity is the mother of all invention. And that's what happened. We wanted a cheap way to do it. Like the one lady there asked, she wants to measure the indoor black carbon. And what it helped us, unexpectedly, the women seeing the filters dark, and they're asking, is this what we are breathing? And I go to every cook stove intervention, they say, oh, the women love the cooking with the smoke. We didn't find that. When she saw the junk she was inhaling, they were all clamoring for our cook stoves. So it was really, in the cook stove case, we know the cook stove is what is causing a majority of this brown cloud. And we know the black carbon from the cook stove is landing on the Himalayas. What we don't know is how much of a warming effect, and that's what we are trying to find out.
Okay, thank you very much. Thank you for coming and speaking, and thank you all for coming and covering this. Our next press conference will be at 4 p.m. It's going to be about Glory and Aquarius, which are upcoming spacecraft that will be launched that will be doing Earth observing. So hope you'll come back then. That's at 4.